Okay, so we're going to continue talking a bit with regards to electrostatic actuation today. We're going to be talking about capacitive comb drive actuators. So a capacitive comb drive actuator works by increasing the area of overlap between capacitor plates. So everything that we talked about on Wednesday was all about how we could manipulate the gap seen between plates. Now we're talking about manipulation of the area. So I'm going to attempt to draw a microstructure here. So something akin to this. So I'll draw another finger or two here in a moment. Excuse me. So this is going to be my stationary electrode. And then interdigitated between these stationary electrodes, we will once again have some movable electrodes or fingers, however you want to call them. Something akin to this. Where these are our movable fingers, sorry. And as we talked about when we were dealing with using Combs drives to sense things, there is some fringe capacitance CF, sorry, that occurs between the end of the fingers and then that gap there. That's typically very small. So we tend to not worry about it. And then we have some capacitance here, which I'm going to call C overlap. Sorry. That is, goodness, I didn't want to erase that much. C overlap. There we go. Um, where this distance, sorry about that, is our distance between the plates. This is going to be our X dimension. And I didn't really draw these super well, but there is some height here. And then let's assume that there's some amount of overlap between those fingers as well, which would be in this particular dimension. Okay. So when a finger of the comb drive moves by some distance x, the capacitance formed by a single finger-to-finger overlap is going to be given by the following relationship. And so I'm going to say that we'll have C overlap is equal to epsilon. And now, typically speaking, I would have my area for capacitance. So that area is going to be formed of my height plus L naught, which is the initial overlap length, plus X, where we're assuming that the positive X direction is causing that amount of overlap to be increasing, okay? All of this is going to be over that nominal gap distance D. And then we're going to add to this some fringe capacitance CF, which I said previously we're going to wind up neglecting for the most part because it's going to be so much smaller than our designed overlap capacitance because the area of overlap is incredibly small. And typically speaking, the distance between those two regions is typically large, okay? So from this, the total device capacitance I'm going to make a note here, neglecting CF will be C total is approximately equal to epsilon n times H L naught plus X all over D, where n is simply the number of overlapped fingers that we have. So it should scale linearly depending on the number of fingers. And then we can use this relationship to determine the force generated by our device under a DC bias, okay? So under DC biasing conditions, our electrostatic force, F sub E, is going to be the absolute value of the derivative of our stored energy by our capacitor with respect to our displacement X. And so this is going to come out to be 1/2 times the derivative of our capacitance as a function of position with respect to the X direction, multiplied by the square of our bias voltage. And this comes out to be epsilon, sorry, that looks shittier than normal, NH over 2D times our bias voltage squared. So once again, we can see something here. This electrostatic force is independent of our plate displacement X, okay? So the amount of force generated doesn't matter particularly how much we draw our fingers in or out of the device. And it is also always acting to increase the overall capacitance, okay? One of the principal advantages of a comb drive actuator like this is that the drive electrode can be electrically isolated from a signal electrode. So I'm missing some of my notes here. I'll find them in a second. So what I mean by that very specifically is we can effectively set up multiple different orientations of fingers. So we might have something like this. This is going to be just a quick and dirty kind of diagram, as it were. But let's say that I had a top-down view, something like this, where I've got a plate. I've got a bunch of interdigitated fingers. On this side, I'm going to put some interdigitated fingers like that on the other side as well, although I've only drawn one portion of the fingers. Like so. Let me draw some fingers here in between for what it's worth. Some over here as well. Like so. So I'm going to put a label on this side. This is going to be a set of drive electrodes. And this is also going to be a set of drive electrodes. I'm going to put a very thin kind of spring right here attached to some anchor point. I'll do one up here as well. And then on this side, I'm going to draw some fingers. I'll only do a couple of them just for brevity's sake. Imagine the same thing down here on the bottom. Hopefully we can make sense of this thing. I'll explain what I'm trying to get to in just a second. So I've got a set of sense electrodes on the top and bottom. And this guy, I'm just going to put sense up here as well because I didn't give myself really enough room. So effectively, what I'm trying to depict here is we've got a system to where, let's say that I apply a bias voltage across the drive electrodes on the left-hand side of the device. That is going to try to draw that entire microstructure in the center over to the left-hand side. Transversely, if I turn that set of drive electrodes off and turn on the set of drive electrodes to the right, it's going to try to draw that central microstructure over to the right so that I can have some level of oscillation back and forth, okay? Well, what's going to happen with those sense electrodes is that we are going to see that the gap between these guys is constantly changing. So this is a way for us to form a different type of variable capacitor where we can potentially get pretty large capacitive tuning ranges just depending on how we choose to orient our fingers and all of that kind of good stuff. So we won't necessarily be restricted to having only an absolute maximum of 50% increase in capacitance. And we can either make this, we can make this very large nominal capacitance by including a whole bunch of fingers, or we can make it a very small nominal capacitance by choosing to use only a small number of fingers on our sense electrodes. So this is a pretty popular RF MEMS variable capacitor design. We're going to see towards the very end of the class that something similar to this can effectively be used as a gyroscope as well. That's going to get into a lot of fun frequency domain math that we'll worry about in a little bit, but you'll wind up seeing something like this as well. So give me just a second because I feel pretty strongly that I'm missing some notes here, and I want to talk about something else that's related specifically to this. So I want to just see if I might have them elsewhere in my binder, and if not, then we'll just figure it out. Put them in the pocket. No, okay. So I'm gonna halfway kind of wing this. So we'll be working together. If something seems suspicious, it's probably because I've got it a little backwards, but we'll talk our way through things. Jordan, yes.
I guess this is more pressure for control, but it's like with this sort of setup, you can easily use those sensing electrodes for like a feedback mechanism, just so you can read out what the live position of this.
Yeah, absolutely.
So how often with these sort of connect systems do you actually need that? Or are they well behaved enough based off what design work we can do that they actually you don't necessarily need?
So I tend to think what you're asking about seems like a very legitimate thing. So like if we're talking about how we do like 4-wire motor control where we need to know what the position of the rotor is with respect to the stator and all of that kind of stuff, like that's what I'm thinking about when you ask that question in my head. I don't know how often that is exactly needed in a particular MEMS system, just because for the most part, these spring structures are fairly rigid, so they're going to move back to their position pretty easily. There shouldn't be a lot of quote unquote play in these springs because they're beams, not coiled up pieces of wire. I like the idea, but I don't know how, I haven't heard of it being used in that way before, essentially. But I can definitely see how you could easily do that because you have a specific way to measure the displacement. Yeah. So when we derived everything right here, we put things in terms of V bias squared, where we were under the specific conditions that we were doing DC biasing. But there's nothing necessarily stopping us from using this relationship to figure out if we had what was going on if we had, say, for instance, AC biasing or some combination of a DC signal with an AC part superimposed on top of it. So let's just kind of see how that shakes out really quickly. So we've got this. I really wish I had my notes here. I feel like I'm going to screw this up, but it'll be okay. If I have to come back and fix it, it'll be what it is. So we've got our force effectively, and it is dependent on the amount of bias voltage that we are applying. So let's say, let me write that back down here. So we have FE is equal to, what was that? Epsilon NH over 2D. Times our bias voltage squared, right? So we have fairly simple proportionality with a DC signal. Let's say that instead we had some bias voltage that was time varying, right? Where it had some DC component plus some AC magnitude, and we're going to do cosine, let's just call this omega t for lack of a better term, right? Well, if I squared this bias voltage, what's going to wind up happening, right? So V bias squared, I'm going to have I'm just going to FOIL this out old school style, VDC plus VAC cosine omega t multiplied by VDC plus VAC cosine omega t. Multiplying this stuff out, I'm going to get VDC times VDC. So I'll have a VDC squared. Then I'm going to have a VDC VAC cosine omega t. I'm going to have another VDC VAC cosine omega t. So I'm going to add those guys together in a moment. And then I'm going to have a VAC squared cosine squared omega t. So let's take an intermediate step here before I play around with this math a little bit more. So I'm going to have a VDC squared plus twice VDC VAC cosine omega t. And now I'm going to use a trig identity to kind of break up that cosine squared into something a little bit better. So I'm going to put that trig identity over here to the right. For those of you that have had me in circuits classes, you've seen this before for better or worse. But essentially, when I have cosine of some angle 1 multiplied by cosine of some angle 2, this is the same as cosine, excuse me, 1/2 cosine of angle 1 minus angle 2 plus 1/2 cosine of angle 1 plus angle 2. And in this case, angle 1 and angle 2 are both just omega t. So what that's going to do is that's going to give me another term over here. I'm going to have 1/2 VAC squared, and then I'm going to wind up having a factor of 1/2 VAC squared times cosine of twice omega t. Rearranging things just a little bit now, I'll have VDC squared plus 1/2 of VAC squared. So these are both DC terms. So this is some constant force. And then added to this, I will have a twice, or this is going to give me related to some constant force. Then I'm going to have a twice VDC VAC cosine omega t. So this is kind of a mid-frequency thing. And then lastly, I'm going to have a twice, excuse me, 1/2 VAC squared cosine twice omega t. So what I'm trying to illustrate here, I'm probably doing it rather poorly because, like I said, I didn't remember to bring those particular notes, is that if we apply an AC voltage to our system, the force that's generated by that, or if we apply a combination of AC and DC terms, the force that's generated is going to be a combination of AC and DC forces, right? So we have to be a little bit careful, as it were, about what bias voltages that we might apply, because we have to give our mechanical system enough time to react, per se, right? So let me think about how to put this. Essentially what we would see for our electrostatic force generated by our capacitive comb drive transducer would be epsilon NH over 2D. And then I would have that whole voltage thing there. So VDC squared plus 1/2 VAC squared plus twice VDC VAC cosine omega t plus 1/2 VAC squared cosine twice omega t, where I'm just going to break this down a little bit. Epsilon NH over 2D times VDC squared plus 1/2 VAC squared. So this is a constant force. Then we'd have NH over D times VDC VAC cosine omega t, where this factor of 2 right here and that factor of 2 right there cancel each other out. And so we've got an oscillating force, so an AC force at 1 omega. And then we potentially also have a epsilon NH over 4D multiplied by VAC squared cosine twice omega t. And this is an AC force oscillating at twice of our excitation frequency. So,
Sorry, can you explain how do you cancel the epsilon on the middle term?
oh, I shouldn't have. Thank you for that. It shouldn't have gone away. Thank you. I just missed it. So I want us to look effectively at the magnitudes of what's going on here, right? Realistically, we should see that the DC component of our force is actually going to be the largest part if we only had a pure AC system, right? So pure AC excitation on our drive voltages, that middle term would wind up going away. We'd still have some small DC portion, but then we'd have an even smaller AC portion because we'd be dividing by a factor of 4 instead of a factor of 2. So we can generate relatively large DC forces, but as we try to introduce AC signals in our drive system, the level of the force generated by our actuators is actually going to decrease. There are some frequency dependent relationships as well, but I can't remember what they are, so I'll just move on for right now. Absolutely. So yeah, why couldn't I have a DC signal with an AC, or excuse me, an AC signal with a DC offset and apply it to my drive electrode? I mean, like function generators can literally do exactly that. Yeah. Trying to think. I'm frustrated because I don't have those notes and I'm trying to think of where to go from here. Because I don't want to necessarily jump into an entirely different topic and circle back around. I know this is rather early. Let's call it for today because I don't want to jump into something else and screw that up. And I actually want to go back and find those notes so we can start here and I can make better sense of this. I apologize for my lack of preparedness. I literally have no idea where the hell I put those notes.